Right. So in any case, so let's just remember what we have said yesterday. I mean, we have started with kinematics. We are going to do kinematics in 3 dimensions later in the next week. But I started from there because, I mean, the essential concept is the position vector and whatever. Everything is actually deduced from this. Let's remember what we do. In kinematics, we just define the concepts of position, velocity, acceleration, and things like that, just kinematics concepts. This is just mathematics, so everything that we say is going to be 100% true. There is no approximation, no anything like that. But we just stress on some of the things in here. First, we choose a reference frame. Without a reference frame, we cannot define what a position is, right? So that should have been defined. We can choose them in any way we want. I can choose the reference frame for that particle, for example, like that, with the x-axis pointing leftward and with the origin being like this. That's possible, right? So the motion that you are going to describe is going to be described with different mathematical numbers, but it will still be the same motion, right? Let's just keep this in mind. Sorry. So in any case, we define the position as, well, just the position, the x coordinate, and the displacement is basically the change in the x value. And this is something that I have stressed. These are essentially vectors, but the real position vector would be obtained by just, I mean, as a vector. So I have to multiply this position with the I unit vector. We don't use this notation in here because, well, all vectors contain this thing. So since we are very lazy, we just drop this I unit vector from our equations. In essence, what we are doing is we are expressing a vector by a scalar, right? In reality, this is the position vector, but we express this vector by this number, which is its x component, okay? So we're dealing with the scalars, but essentially we're expressing a vector, right? So in 3 dimensions, we need to use the full vector notation. So that's going to be important later, but for kinematics in 1 dimension, we can deal with the kinematics by just dealing with these numbers in here, okay? So let's continue then. We have position and displacement is basically between two moments. Again, it's not important how the object moves from this initial position to that final position. It can move like that. So we're not talking about the total distance in here. It is basically the displacement. So it's not important how the how the particle moves between these 2 instants of time, right? So I'll just call the Ti and Tf are the, let's say this is the initial time. This is the final time. And the time difference, delta T, is defined like that as usual. And the ratio is basically the average velocity. So let's just call this V bar. Let me use this ordinary V, but usually I'm going to use this notation for V because I don't know, I like it that way. But for now, to distinguish things, I'm going to use this notation. So that's the average velocity. All right, let me write delta. First, write down the expression. So that's the average velocity in the, let me write it in mathematical notation like that, in the Ti-Tf time interval. So we have a time interval. So, I mean, between 2 points in time, we talk about the average velocity between 2 points in time. Right? So in any case, so bar in here expresses the fact that this is an average. So, I mean, this is one of the notations that we use for average quantities. And in that case, some of you might be wondering what kind of an average is this? Let me just say that this is actually a time average, which means we're going to define the instantaneous velocity in a moment, but let me just say it like this. So if this is the time axis, let's say, right? So that's the initial time, that's the final time. If I divide this time axis into small intervals, each with equal length. So I basically just choose some points in time in here, which are equally spaced, let's say. And if I compute somehow the instantaneous velocity at all of these positions, the arithmetic average of these velocities would be the time average of the velocities. And it is that, when we say average velocity, it is that time average, right? So somehow, if I make a sampling of the velocity at equal time differences, then their average would be the average velocity, right? Whatever. I mean, if you are confused by this, just ignore that comment, okay? All right. All right, I couldn't close the parentheses, all right. Sorry about this. So we call this as the average velocity. So I'm just going to be a little bit quick in here because I know that some of you have seen this before. If you haven't seen it, then probably you have to look for these kind of things in from the book. So what we do is first draw the position versus time graph. Okay, so in any case, that's basically some kind of a graph like that. So I'm going to draw it like this. Sorry about that. All right, it's something like this, right? So let's say that the initial time is this, and that's the final time, TF. So what we do is, all right, so let me just choose it like that so that I can have a better picture in here, right? TF. Okay, so what we do is we just choose mark the points where the object is at different, at these two times, right? Let me kind of show it like this. So we have the initial time in here, and there's a corresponding initial position. That's the final time in here. That's the corresponding final position. So let me write XI and XF in here. Okay, obviously. So let me say that that difference in here. So let me actually show it with an arrow in here. Because this is a number that can be positive or negative. So let me kind of show it like that, but I'm not really I don't want you to get confused. So that difference is delta T, okay? So if we then draw the line that connects these 2 points, then delta T is the horizontal part of that line, so I couldn't draw this. And delta X is that part of that line. So normally we choose delta T to be positive, but there might be some situations where this can also be negative as well. But in any case, I mean, in all the applications, the delta T will be positive, but delta X might be negative as well. In any case, so V bar in here, right? V bar is delta X over delta T. So that's basically the slope of the line connecting, let's say, 2 points on X versus T graph, right? Let me just stress on this fact. So that's basically the mathematics in here. This graph is not the physical picture. we're just somehow plotting the position as a function of time. So we are basically giving a meaning to the average velocity on that graph. So on that graph, therefore, the average velocity appears like the slope of that line in here. Okay. So that's it. We don't have anything else to say for the average velocity, but we use this to obtain the concept called the instantaneous velocity. All right. So let's then, let me just put it as a title in here. So that's the instantaneous velocity. It's a skill to be able to write this word actually. So instantaneous velocity. Continuous is another word that I have to be very careful in writing. So instantaneous velocity. So that's basically not at an interval, but at time t. Okay. So we actually define it like this. So I'm going to use this symbol. Now, you haven't seen these kind of concepts in calculus yet, if you're taking the calculus this semester, but there's some kind of a limit concept in here. So basically, this is the average velocity, but when the time interval is basically goes to 0. So let me, first of all, write it down like that. I'm not going to do any limit calculations in here, but I'm just going to use some common sense in a way to derive some certain things. So let me just say it like this. The limit of average velocity when the time difference delta t goes to 0. Okay, I mean, we usually show it like that, but basically what we do is we just compute this expression, I mean, as a function of delta t perhaps, and then we actually analyze what happens to that expression when I choose delta t to be extremely small as possible. As when it goes to 0, this expression actually approaches some numerical value, and we would like to find what that numerical value is. It's called the limit. In calculus, you are going to do lots of these kind of limit calculations. Again, I mean, for us, the important thing is the concept actually. So on the position versus time graph, it looks like this. So that's position time. Let me draw the graph like that, right? So what we do is we have a certain time, t, now, and then we choose some delta t in here. And so as a result, we look at the time t plus delta t. So we get another point in here. And then we draw the line that passes from these 2 points that passes from this object. So the slope is still the average velocity. It's delta x over delta t. But now we just change delta t progressively. So we make it in such a way that the second point basically approaches to the first point. So I imagine that I choose this point to be as close as possible to that point, in which case this line is going to change, but it's going to approach to a certain line, and we're basically using this expression to denote this. Okay, so in mathematics, well, this is the mathematics. That's the algebraic expression or calculus expression for that thing. But on xt graph, it's basically corresponds to the slope of the tangential line. Okay, so first of all, I'm just going to take 30 seconds of your time because this is like the end of the airdrop period. So I need to check something if there are people who need approval. So let me check this. Sorry about that. All right, so nobody needs my approval, apparently. All right. So I'm back. Veritasium video. So I don't follow Veritasium, if that's a question to me. All right. In any case, so well, on the XT graph, right? This basically what happens is that we basically have a certain time. Okay. So again, there is only one point on the graph in here. The line that we obtain would be the tangent line. Okay. So that's the tangent line. So we have a single instant of time. And on the position versus time graph, we draw the line tangent to the graph in here. And the slope of that line is basically the instantaneous velocity. And we have a new notation for that. So that's basically shown like that. Okay. So let me go back to that expression. So we just call this as, with a special symbol, we just call this as, sorry about that. I'm going to write this thing down. So the instantaneous velocity is basically written this time now, dx over dt. Okay. So here, dt is called the infinitesimal change in the value of t. So it's essentially delta t, but let me write it down like that. That's the same thing as delta t, but delta t is extremely small. Yeah, it's hard to describe this thing, extremely small. It basically expresses the idea that we just take the limit where this quantity goes to zero. So that's the meaning of infinitesimal. But still, it is a change. So dx is also, it's an infinitesimal change. In x this time, right? It's again a change in x divided by a change in t, just like in the average velocity, but we are telling that this quantity is essentially zero, right? Let me actually note it like this. This delta t in here and this delta x in here, they are essentially zero, but not exactly zero, right? So if they are not exactly zero, then I can take their ratio. And if they are very close to zero, then that ratio is going to give me the instantaneous velocity. So in any case, in mathematics, there is a certain way of actually computing these things. It's basically the limit calculation. We don't worry about this thing, but whenever you see this symbol, whenever you see dt, you need to understand that, well, this quantity is essentially zero, right? So we just call it as an infinitesimal. So delta t or delta x, these are basically finite changes. But a finite can be anything, like it can be 1 second, 2 minutes, 1 year. It just depends on your choice. It can be very small as well. But when we say dt, it means that it is so small that it is essentially zero. All right. So in any case, so there is a certain name of for this quantity in here. We call this as the derivative of x. It's the derivative, right? Let me write this correctly so that it can be clearly read. So the derivative of x with respect to t is derivative of the form 0 over 0. I don't understand the question. We're not taking this ratio, but we are taking the ratio of two small numbers. But if you think of it as the type of limit, yeah, that's the type of limit. So the derivative of x with respect to the time. Unfortunately, this is a subject in calculus. So you haven't learned this part of calculus yet, so probably you're struggling with the limit concept now. But I think within this semester, we are going to see the derivative, all right? All right. Okay, so I'm not going to make any comment on the chat screen. But in any case, I mean, when we say this, right, it's essentially zero. I mean, there is a proper way of doing this. So it's basically the limiting thing, taking a limit in mathematics. But physically, if you think about it, we can just say that, well, these are so small that it is kind of negligible compared to other quantities of interest. What other quantities, for example, with respect to t or with respect to x, right? So these are these quantities in here. So again, you can think of it like this. So x can be considered as a function of t. In calculus, we actually do this. We sometimes write an explicit function, and this is also what we are going to do in here. So I'm just going to show it like that. So as a result, dx is basically the value of x evaluated at t plus dt minus the value of x at time t. You can also think of it like this. And well, dt is basically the difference between these two. So it's the difference between t plus dt. Well, it's the difference between the time between these two time values, if you want, right? You can also think of it like that. And so therefore, the derivative is, it's basically this ratio, right? So if dt is very small, infinitesimal, then this is also supposed to be infinitesimal, and we get this. Okay, so in any case, so in calculus, the instantaneous velocity is equal to the derivative. On the x versus time graph, the derivative appears like the slope of the tangent line, right? So as a result, we have these two different mathematical ways of looking at this concept in here. Okay, so normally I would basically wait for you to see this concept in calculus, and then after that we would start using the derivatives in that course. But however, I mean, the derivative operation is not that difficult, actually. So as a result, at least for some simple functions, we can compute what derivative is. And so as a result, that's what I'm going to do. So I'm just going to think of it like this. So suppose, let's say, consider the power function. Let's say f of t, that's equal to t to the n, where n is just a constant in here. Consider the power function, right? What is the derivative? Derivative df over dt. This is actually quite simple. And I'm just going to do the calculation, right? Thank you very much for your answer. All right, so consider the power function, right? N is just a constant, so that's important. So how do we find the derivative? That's basically, first of all, we need to compute the change in the difference in f value. So basically what I do is like, think of it like this on the function versus time graph, right? Think of it like that. I have this time in here. Now I'm exaggerating. So I have another time, which is t plus dt. So the value of the function at that point is known. So that's f of t. And the value of that function at that point is also known. So that's, yeah, let me draw f in here. So the value of that function at that time is f plus dt. So that difference in here is df, right? We know how to do the calculation. The only difference in here is that this dt is very small. So that's something that I need to take into account, right? So I need to just compute df. So that's the value of at time t plus dt, sorry, minus the value of the time at time t. So I need to take the power of this and then subtract this. So you can see that I need to use the binomial formula in here. And that's basically as simple as this. However, I'm just going to do it like this. I'm just going to write the binomial formula in here. Sorry about this. I'm just going to write this thing down. So binomial formula. Right, let me write it down like that. A plus b to the power n is a to the n plus the combination of n with 1 times a to the 1 less power b plus n combination to a n minus 2 b2 and so on. Okay, so this combination is basically n. This is n times n minus 1 divided by 2, and so on again. So, I mean, n k combination is this. Basically, it is n factorial divided by k factorial n minus k factorial. Or if you want, you can write it down like this. It's just the product of, yeah, sorry about this, undo. Sorry, I'm going to write it down like this. So I'm going to write this thing down as the product of the k numbers, k successive numbers that end up at n, right? So there are k numbers in here divided by k minus 1 dot 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 1. So instead of factorials, probably it is better to write this thing down in here. So that's essentially what we do, right? N1 combination is n divided by 1, essentially. You can think of it like that. This n2 combination is n multiplied with n minus 1 divided by 2, and so on, right? It just goes on like that. Okay, so you know the binomial formula. What you don't know is that I can apply this formula even when n is not an integer, is not a positive integer. So that's important. So we can still use this formula when n is not a positive integer. Okay. But in that case, let's say it like this. In such a case, let me say the series does not terminate. Right? Let me say it like this. There are infinitely many terms in there are infinitely many terms in the expression. Okay, so what happens is this. So I have said dot, dot, dot in here, right? I didn't specify where it ends. It appears that this ends only when n is a positive integer. But if n is not a positive integer, it doesn't terminate. So in mathematics, people call this as a series. It's basically a sum with infinitely many terms. It's basically some kind of a limit calculation as well. Again, we are going to see this in calculus. We have nothing to do with this, but usually in physics, we are going to meet situations where, for example, one of these numbers is very small. Let's say b is small in here. In which case, the terms that containing b and b squared and whatever, these are also going to be small. So in such a case, this kind of a series can actually make sense. And usually we are going to approximate this by the first two terms or something like that, right? This is what I'm going to do in here. But this is something that you need to keep in mind. I don't know. I mean, you might have like kind of expressions like the square root of 1 plus epsilon, for example, where epsilon is a very small number. So in that case, you can think of this as the 1/2 power of 1 plus epsilon. So as a result, you can write this thing down as just like an ordinary binomial expansion. This is 1 plus 1/2 of epsilon plus n is equal to 1/2 this time. So you can write this thing down like that. It is 2 divided by 1 times epsilon squared plus 1/2, 1/2 minus 1, 1/2 minus 2 divided by 3 times 2 times 1 times epsilon cube and so on, right? I mean, you can, there is this kind of an expansion and this basically converges, but that part is not important. Usually you're just doing this as an approximation, and so as a result, you just keep only the first two terms, all right? Let me just say it like this, okay? So what happens in here is that in our case, we just have something like that. Yes, this is called a Taylor series, right? It's called the Taylor series expansion of this. I mean, in calculus, you are going to see lots of interesting properties of such series. You will be interested in what is the limit and things like that. But as physicists, we usually do not be concerned about this. We usually ignore these. Because if epsilon is small, then epsilon squared would be much smaller than epsilon. So as a result, we can easily ignore these. So we will be basically concerned about this approximate expression in here. Okay, let's come back, all right? That was a digression. Let's come back with that expression, okay? So I have a binomial expansion in here. N might be a positive integer like a square, or may not be 1. So it can be -1 or 1/2, can be anything. Don't worry about these kind of details. So when I expand this, I get the binomial expansion. So I have the first term t to the n. The next term is n times t to the n minus 1 times dt. Next term is n minus 1 divided by 2, t to the n minus 2 times dt squared. And yeah, it just continues like that, all right? Let me just write one more time. That's 3 times 2, t to the n minus 3, dt cube, and so on, okay? Minus, well, we have t to the n in here, okay? So this cancels with that. So what is left is basically an infinitesimal quantity, but this infinitesimal quantity has a dt in here, the square of dt in here, and the cube of dt in here. Can I show the graph y? Let me show it later. Okay. So, I mean, so if we just write down this expression in here, so the change in infinitesimal change in the value of f is n times t to the n minus 1 times dt So that's small, infinitesimal. So let me also write down this next term in here, dt squared. So this is small, that's infinitesimal. All right, because there's dt in here, which is almost zero. But this is even smaller. So much more smaller than the first term, right? I'm just going to draw this again. Than the first term. Okay. The reason is that the first term contains dt. This contains dt multiplied with dt. So if dt is small, dt multiplied with dt is even smaller, right? So as a result, next to that first term, I can easily neglect this, right? Neglect. Mathematicians just basically eliminate this term because of some reason. They just eliminate it at the limit. Physicists usually neglect at that stage. They say that, well, this is much smaller than the first term, so it is ignorable, so just neglect it, all right? But at the end, the whole calculation is actually an exact calculation, right? There are these other higher order terms in here. There's a dt cube in here. This is also actually much, much smaller than even the second term. So as a result, we can never mention about this. Okay, so in any case, but let's do the way that the mathematicians do. So we just take the ratio, right? We have to divide this by dt, in which case this dt cancels, and I get this term in here, all right? And then from this term, I get this t to the n minus 2 times dt in here. And then whatever, in the third term, we get dt squared. So as a result, from the infinitesimal term, when I take the derivative, when I take the ratio, I get a finite result in here. So that's finite. So this term is infinitesimal now. And this term is even smaller than the infinitesimal. Whatever, I don't want to write this thing down. So the mathematician at that stage says that, well, all of these terms go to zero in the limit when you take the limit. And so as a result, we are stuck with this first expression, okay? But as I said, physicists actually eliminate these higher order terms at this stage. Mathematicians eliminate them after taking the ratio, right? But in any case, you can actually view it in any way you want. So the essential idea in here is this, right? Essentially, right? In the binomial expansion, t plus of delta t, right? What we do is we just keep the first term, which is finite, and we just keep the second term, which is like the next smallest term. We just ignore the rest. Okay. I mean, this is how physicists actually handle these kind of expressions. We ignore the rest because when delta t is extremely small, these are much smaller than this, this small term in here, right? So in any case, so therefore, let's say it like this, delta f divided by delta t is basically this expression in here, t plus delta t to the n minus t to the n divided by delta t. So this expression is now approximately equal to n times t to the n minus 1, delta t divided by delta t, which is n times t to the n minus 1. But in any case, we just get an approximate equality in here because we have ignored the remaining terms. And then we say that, well, this becomes exact in delta t goes to 0 limit. Okay, So this is how we are going to see this in calculus. So I kind of summarized it. I mean, physicists usually do this by ignoring terms. So let's say it like this, in summary, right? So let's say it like this, if f of t is equal to a power function t to the n, then the derivative of f is also a function. It can be obtained by multiplying the power with the function with the one less power, all right? I can use a dimensional analysis in here. Dimensional analysis. Okay, so f has the dimensions of time to the power n. So df over dt, I basically divide f, something with the dimensions of f, with the dimensions of time. So therefore, it should have the dimension of, yeah, let me write it down like that, all right? I'm just dividing it with a time to the power n with time. So as a result, the resulting thing should have the dimension of one less power. And this is indeed what we see, right? So as a result, at least this part of the derivative formula, I could have deduced by using dimensional analysis alone. But in any case, I couldn't find what the coefficient was. But in any case, I mean, this is the one rule that we are going to use for computing some certain derivatives. Okay. So yeah, it's 25 past. So as a result, let me give the break in here. Let's meet again at 1:40, sorry. So let me write this note in here. So let's meet at 13:40. So there are some comments, but I don't know if all of them are meant for me. Okay, so why hard to follow? Well, it is hard to follow. I mean, these are some advanced concepts from calculus. So I'm kind of giving these concepts to you without explaining what everything is. So if you want to understand it, then just wait for the appropriate time comes in calculus course. All right, but here I'm just basically going to follow this kind of rule. I kind of deduced it, but you didn't have to follow the whole derivation. So, but I'm just going to use this rule in here. So if the function is that power function, then its derivative is this. So as a result, if the velocity has a t to the n dependence, sorry, if the position has t to the n dependence, then the velocity would have this much dependence on time. So that's the simple rule that we will be following. Okay. So let me stop the recording. Sorry. I cannot stop the recording.